All right, so how you guys doing today? Good, perfect. So we have exam two next week, this a week from today. So assuming you guys in Wednesday pod, so it'll be a week from today for you for exam two. If you're in a Friday pod, it'll be 9th of April. Okay. So what I'm gonna do is I'm gonna finish up the chapter 6 like really fast today, and I'll move on to the review right away today. So we can possibly have some time for review even from today and Friday and Monday, so 3 times. Okay, so it'll be good time we can study for exam 2 together, and also you can also watch it on the YouTube channel as well later. Okay, so please watch those YouTube channel videos. When in the class, I'll be read home. Okay, so let's finish up the chapter 6 real quick. So we talked about the electron configuration. Form. So here's a couple things I just want you to remember. So this is the first period, first row on your periodic table. This is S block. Okay, so I'm gonna put this in the S block, and then if you look at the periodic table, first and the second column is also S block too. Okay, and then you see this like a big block between the S and this is a P box. So the last six columns in P block, except the first period, which helium is still S block. But from the second row with the last 6 columns is a P block. Okay? And this S and P block, there's D block between, and from the here. Okay? So this is the something I want you to remember. We have a F block down here, which obviously I'm not gonna do this, so you don't have to worry about this one. Okay? So I just want you to know how to make electron configuration form for each different elements. Okay? So for example, you wanna do phosphorus over here, P, phosphorus over here. You're gonna read this periodic table, will be given on the exam too, from left to the right, top to bottom. Okay? So left to the right and top to bottom. So you always start from here, hydrogen, which is in the top left corner here, right? So, and if you have each period, first, second, third, fourth, you just need to put 1, 2, 3, and 4, which is your energy level N. Okay? So this is the first quantum number we learned in last time. It's a principal quantum number. And just one more thing I want you to remember is even though this row is in 4 and 4, this D block starts with 3. Okay? So we're gonna talk about this Y next chapter after exam 2, but for now I just want you to remember it starts from not 4, even though it's the fourth row, this is 3, and this is 4 and 4. Okay? So, but D is 3. Okay? So in this case, let's try to do phosphorus over here. So I'm gonna count the electron from here. So it'll be 1, 1s1, 1s2. Okay, and then so it'll be 1s1, 2 here, and then now your second row is 2s block, 2, 1, 2. So it'll be 2s1, 2, and then now this is in second row in p orbital. So it'll be 2p. Okay. In p orbital, as you know, we have a 3 orbital diagram because it's -1, 0, 1. So it'll be 1, 2, 3, 4, 5, 6. Because each box can fill with the 2 electrons. So in max, in this whole 2p could be 6. Okay? So it'll be 1s1, 2, 2s1, 2 right here, 2p, 1, 2, 3, 4, 5, 6. Okay, so we're done up to here. Okay? Up to neon. Okay? And now the next row is 3. This is S block, the 3, S, 1, 2. Okay? And now we get to this one over now. So it'll be 3p, 1, 2, 3. So that's it. Okay? So if you do this one, that is the electron configuration form for phosphorus. Okay? This is how we read the periodic table when we section elements in the several blocks, S and P and D over V. So this is really long version of the electric configuration form. So you can actually have a abbreviated form that is using the one in the last column, which is noble gas. So if you try to maybe make the electric configuration form for phosphorus over here, just look at the one in the last column, but just one row above. So in here, in the same row, we have a last element in the last column, which is noble gas, is argon here, but one above. So it will be neon, right? So then you can just put neon in the bracket, and then neon will abbreviate this part over here, whole thing. Because if you make the electric configuration form for neon, it will be 1s2, 2s2, 2p6. It's all here. So in this case, you don't have to do all this. Just put the neon in the bracket, and you can just start from here, which is what? 3s12 and 3p123. So this is much shorter, which is easier to put. Okay? Does it make sense? Okay. So can you guys try? Can you guys try sodium? Let's do longer version and shorter version together. Okay. Let's try to make the electric configuration form for sodium here. Let's do long version and short version together. Okay. About 1 minute, we'll do this together. Okay. So count the electron from left top corner to the right and down. Left to the right and top to bottom. All right, so here's the thing. So we get to from here to here, okay? So it'll be 1, S, 1, 2, 1, S block, 1, 2, okay? Just to make it small. And then this is now we get to the next will be 2s 2, and this is in P block, so it'll be 2p 1 2 3 4 5 6 6, and now we got to this one, which is 3s1. So this is the long version of electric configuration for sodium, but you can also make it abbreviated for this one up to neon, so you can just say this is also that. Because the neon has that all 1s2, 2s2, 2p6 here and bracket, so you can abbreviate it. Makes sense, right? Okay. Do you want to do one more, or can I move on? One more. Let's do one more. Okay. Maybe can you guys try chlorine here? But short version, because I want to save time here at this time. If you know how to do the long version, you'll be able to do the abbreviated form too. So the chlorine is the second last one, and the third period. Yeah, let's do abbreviated form. Okay. Alrighty. So here's the thing. So I'm gonna look for the noble gas just one period above on chlorine, so it would be not argon but neon. So I'm going to copy neon here, and then I'm going to start from here because we already done here by putting neon on the bracket. So it'd be 3s12 and 3p 1 2 3 4 5. So it'd be 3p5. That's it. Okay. We good, right? All right, so if that is good, I'm just gonna do one more thing and we're done with the chapter 6, okay? So, like I said, the sodium here will be what? Neon in the bracket, and will be 3s1, okay? And then Here's the thing. Sodium is an alkali metal. So it's group 1 element, right? So if that is the case, when this sodium goes into water, they become what? Ionized. So they become cation. So sodium, sorry, not lithium. Sodium cation. Okay? And then means this sodium will give up electron, 1 electron. Okay? Because if you look at those, except the hydrogen, all metal in the first column, alkali metal, they want to donate the 1 electron to be electronically in the noble gas form here. Okay? Because they are all stable elements in this last column. So we call this noble gas. But for sodium, if they can lose just 1 electron, they can be in form of what? Noble gas in electron configuration form. So they're not going to be neon because they don't have a same proton numbers, right? That's the identity of the chemical. But electron configuration wise, they can be similar to the ones of neon. So that's why alkali metal always give up the electrons, become cation in water. Okay? So if you look at the sodium, electron configuration form for this one will be what? Just neon 3s1, right? For sodium cation, which you have 1 electron is gone, will be just neon in bracket, which is also same as what? 1s2, 2s2, 2p6. Because the sodium cation is the one that lost 1 electron. So once it was 3s1, but this electron is gone. So this is the same as just neon, or you can say 1s2, 2s2, 2p6. But this one is still 1. So sodium cation does not share the same electron configuration because they don't have the same numbers of electrons. Okay? Makes sense, right? Okay, perfect. So can you guys try potassium? Okay. Let's do potassium electron configuration form first. And you can also do potassium cation electron configuration form as well. Let's do short version here. We want to save time. So let's do potassium electron configuration form first, and let's try the potassium cation next. Okay. So potassium is right here. So you need to look at the noble gas 1 row above, which is R right there. So you can use that for abbreviated form of electron configuration. And then let's do it for the cation part too, okay? Okay, about 30 seconds. We'll do this together. Don't worry about it. Okay, so potassium, I'm gonna do here is 1s12, 2s12, 2p6, 3s2, 3p6, 4s1. Okay, but I'm gonna do that the argon, so it will be just argon in the bracket and 4s1. That is the electron configuration form for potassium over here. But the cation means that now it lost 1 electron because it's +1. So what I'm gonna do is just 1 in the bracket and argon is that's it. Okay, because now this electron is gone, become cation. Okay, so means that electric configuration wise, this potassium cation is the same as argon, but chemical identity wise still different, but they can be still similar in the electron structure. Okay. So they can be more stabilized. That's why they always give up the electron in the water and for this alkali metals. So they're very reactive to water. So if you put the alkali metal in the water, they explode. It's lots of energy coming. All right, so that's it for chapter 6. Can I finish this one, or do you want one more and do the review? Can I finish? Okay, let's finish here. So we're finally done. Let's do review, okay, for today. So we can have more time on the review on Friday and Monday lecture. So let's try this one, okay? If you have a solution, are defined as homogeneous mixture of two or more, okay, true or false. Okay. The solution, we define the solution as a homogeneous mixture of two or even more substance. Okay, substance. Okay. The true or false? True. Perfect. Okay. This is what we did here. Solution. So there's one more thing here. So whenever you have more than two or even three or four substance mixture, homogeneous mixture, if you have a one that is abundant over the others, that is called what? Solvent. Okay. So let's say you have a sodium chloride solution, and you're gonna put AQ, means aqueous. Aqueous means it's surrounded by water. So in this case, this aqueous solution, the sodium chloride solution, the water is your solvent. NaCl is your solute. You guys remember this, right? Solution. Okay. So that's true. Okay. All right. So there's another one. You have an electrolyte. Is okay. Can I just say it? So electrolyte is a substance that does not dissociate in water. Is it true or false? So you have one that called electrolyte, and if they don't dissociate in water, if it's the electrolyte or not, true or false? So and for this one, do you remember what this is? Electrolytes. So this is the one that can carry the charge through the system. Meaning, if they do not dissociate in water, if they don't ionize, they cannot carry the charge in the solution. Meaning they cannot be electrolyte, because electrolyte should be able to carry the electrical charge by moving the charged molecular ion in the solution. So if they don't ionize in water, they cannot be electrolytes. Does it make sense? Okay. So that's what it means. Electrolyte means, in the textbook it says the things that become ions in water. It's the same meaning. The things that can be dissociate, and so they can do the motion of the charged particle or the ion, so they can charge the electrical charge through the system. Okay.
So they do dissociate?
They do dissociate, yes. Electrolytes has to dissociate to be in form of ions, because ions will carry what? Charge, either plus or negative. Okay. Make sense, right? Okay, perfect. All right, let's do a bit more the chemical equation like problem. Okay, so lithium carbonate. Okay. Okay. And then you can use a double displacement and try to find out what might be the net ionic equation for this one. Okay. So try to do double displacement and see what product can be insoluble in water, and that will be your net ionic equation. Okay. By the way, I'll give you the solubility rule table anyway, so you don't have to memorize which one will come out from the water or which one will not. I'll tell you now today, but the solubility rule table will be given. Okay? But if you just use a basic rule I've been telling you in the lecture, you'll be just fine anyway. But yeah. Okay. So for this one, do you know why there's 2 lithium instead of 1 for this one?
Because carbonate here is negative.
Perfect. There you go. That's great. Okay. So same here. There'll be 2 chlorine for magnesium because this is just in second column. So it'll be +2. So it'll be yeah. So okay. Great. So in this case, what we're gonna do is once again we're gonna do double displacement here. So you're gonna have a 2 lithium chloride, okay, and 1 magnesium carbonate. Okay. So here's the thing. So there are a couple. Even though I'll give you the solubility rule table, but here's something I want to tell you. You might not even need to look at the solubility table. So if you look at anything that is in first column, like I said, this is group 1 element. We call this alkali metal. It's always soluble in water. So it's always soluble in water. So no matter what bond to that lithium, it's always soluble. So there's no exception at all. Okay. So this lithium chloride should be soluble in water. Okay. But look at this one here. Here's one thing you can try. If you look at the ones in the second group, the second column, okay? So you have calcium, magnesium, and so forth. They're not really, they tend to be soluble in water, but not so much. They always look for the way to be, not to be surrounded by water. And this is a big shot too. So carbonate is not really soluble in water much, okay? So these two makes very good combination that is not soluble in water, okay? You can also find this in the solubility rule table, but you don't really have to memorize this because this is not so or insoluble in anion. Group 2 is not so good at this dissolving water either. So this will actually come in solid phase. So they come out from the water. Okay, so they will precipitate. Okay, and then when they precipitate, that is the one that we're gonna use for net ion equation. Because think about it. If these two dissociate in 2 different ions, like cation and anion, but this still be in ion form, and this one still be in ion form if they're both still in aqueous form. So this will be still in form of a cation and anion, but for our convenience, we just put it together in aqueous there. But for this one, it's totally different now. They're not in the aqueous phase anymore. They become solid. So they just come out from the water, meaning water cannot surround this compound combination. So this is the one that actually did what? Chemical reactions. Because these two didn't do nothing. Okay? So in this case, what we're gonna do is the magnesium 2+ and cation, and this the carbonate 2-, also anion in aqueous form, and now they're gonna form solid. So they precipitate. So this is our net ion equation. So the key point here is look at the solubility rule table, and when you do double displacement, you're gonna have a new 2 products on the right side, right? And look at which one will be not soluble in water, and just use that one to make it net ion equation right there. Okay, so let me rewrite this one real quick. Okay, if you rewrite this one, this is what it actually looks like. Okay. This is what happened. So as you can see, this one and this one, this one and this one didn't do anything. They just still stay as the same in just ion form. But these two combined to be precipitate. So those are the ones that didn't do anything, left and right. We call them spectator ions because they just are watching. They didn't do anything. Then you can just cross them out, left and right, because obviously they didn't do anything. Now they will get you this one. Yeah.
Shouldn't there also be carbonic gas in the?
Oh, not here. We're gonna do it from another example, but yeah.
How do you know when to add?
Oh, there will be the addition of the acid.
Oh, acid.
Acid plus the carbonate form the carbon dioxide and water. Yeah. We'll do that too, yes. That was very good question. But makes sense, right? Yeah, okay. All right. So next one is this one, okay? So let's try to put acid and base. Okay. And then also same thing, maybe we can try to look for net ion equation here. Okay, same, okay. Should do this. So this is the reaction of acid and base neutralization. Okay, so I hope you guys remember this. This is the acid one, this is the base one. Okay. Okay, this will take some time, so maybe 2 minutes. And we'll do this together. Okay, so here's the thing. Let's try to break this down into ions first, because they're all in aqueous phase. So I mean they're all ionized. So let's try to put it on the more full ionic equation. So it'll be H plus Cl minus Na plus OH minus. Okay. So this is what it actually looks like, because they're all ionized in water. But the neutralization is simply you try to remove the what? Excess numbers of the hydrogen cation, which is the same as proton. So if you look at the hydrogen, it's just simply one proton with the one electron. So if the hydrogen ionized in water, it's just same as proton, and then this can be picked up by hydroxide anion to be water. So they can be neutral. So meaning you still gonna have a sodium cation and chlorine anion just still there doing nothing, but these two will combine together, becoming water, H2O. So as you know, if you have a lot of protons, that makes your solution very acidic, because your pH value will be very low. It's negative local concentration of the proton. But they will combine with the hydroxide anions to be neutral as water. Okay. So we're gonna just eliminate the spectral ions on the right both sides, and then finally you can have your net ion equation, just proton, hydrogen cation plus hydroxide anion become water, okay? Which is obviously, as we know, neutral. So water is neutral because when we try to define the acidity or basicity of the compounds, we put water as a standard. So literally water is a neutral standard. Okay? If you're taking, are you guys taking Genchem 2? If you go to Genchem 2, you're going to learn about the auto ionization of water. So that will become 10 to negative 7th of the concentration of each proton and hydroxide anion. That's exactly at 7 at pH. So, but for now, we don't have to worry about it. But so here's the thing. If you look at the acid and base reactions, it is always going to be same. That ion equation is just this one. because it's basically all about the how many proton comes in, how many hydrogen anion comes in, makes how many water there. Okay. So anytime. So if you, even though I say this one, okay, maybe this one. Okay, let's do hydrobromic acid here, and the potassium hydroxide anion. Whatever you do, we know this is acid. We know this is basic because it's an OH there. Still same, always same. The neutralization process, net ion equation is always H plus OH minus water, always the same. So if you know, if you're seeing these two reactants are acid and base, just look for this one. That's the answer right away. Okay, makes sense, right? Okay, that's even easier for. Yeah. Okay. All right. So let's talk about the other one that we slightly just talked already, but this is the other one. Let's try this one real quick. This is the sodium bicarbonate, which is your baking soda. Okay. Oh no, that's okay, let's try to this one. Okay, this is what I briefly mentioned, acid and carbonate compound combination. So you're always looking the carbon dioxide and the water. Okay, this also takes some time. Okay, so this one will be like Cl2. Okay. So yeah, as you can see, the sodium here and sodium chlorine didn't do anything. For this type of question, if you can find out just the product, you can just stop there. That'll be all you need to know for this type. Okay. All right, let's do some calculation problem. Okay, let's try. If you have a 23.5 grams of iron 3 sulfate, and then and this was transferred into the beaker, and that beaker was boiled up to 342.5 milliliter with water. Okay. So when we transfer 23.5 grams of the iron 3 sulfate into the beaker or container, and we fill the water until you get to this volume. So we're not adding this much water, we're adding the water with this one together to be at this volume. So we actually add slightly less than what we see this number here. It's volume because this is together. This one plus water makes this volume. And then the question is what is the concentration of the solution in molarity? So molarity is simply moles per liter. Okay, let's try to do 3 minutes because it will take some time. Yeah. About 3 minutes. This is 4, by the way. Oh. My writing. Yeah, you need to start looking at the periodic table. That's a good sign because you need to use the atomic mass for each element to get the formula weight, and you'll be able to know how many moles you have there. Okay? So it takes about 3 minutes at least. Okay. Coding time 35. Okay, about 1 minute, we'll do this again. So this is actual mass. Try to get the formula weight of this one from the periodic table, and then you can get the numbers for moles, and this is the volume you can have for concentration. Okay, 30 seconds. All right, so let's do this together. So the key point here is the if you have an actual mass in gram, okay, you can divide that by formula weight, which is what? Gram per mole. So formula weight simply means if you have a 1 mole of something, how much it weigh. But if you know how much it weigh, if you divide that number by formula weight, if you can look at those 2 units for mass will be canceled, top and bottom. But this will become a numerator because this is denominator of denominator. So it will tell you how many moles of the compound you have over there. So I'm gonna switch this one to 23.5 gram. Okay, and then now we need to look at the periodic table to find the formula weight of this one. So all you need to do is you need to have a 2 ion here, so it'll be 2 times 55.845 gram per mole, okay, here, and plus you have a 3. Well, you see the 3, right? 3 sulfur, which is 32, okay, plus you have a 4 times 3, okay, 4 times 3, that's about 12 times 16, which is oxygen here. So if you do all that, then it will give you approximately 399.9 gram per mole, okay? So that is your formula weight. By just counting the numbers of each element in your formula and add all of those numbers, and you can get the formula weight, literally is formula weight. And then you can see, once again, grams cancel, you get the numbers moles, it should be around 0.0587, okay? And then it's now, once again, you have this many moles here, and what we want to find out is concentration. So we need to use a volume here, but the problem is molarity is, once again, moles per liter, but this is in milliliter. So 1,000 milliliters is equal to 1 liter. Okay. So if you do the unit conversion, 342.5 milliliter. Okay. I'm gonna put the same unit at the top and bottom, so it'll be 1,001 liter on the top, so they can be canceled. So you can get a number in liter, which will be what? 0.3425 liter. Okay. So here's the thing. This one has to be moles per liter. That's why we're dividing these numbers in moles by ones in liter. So you can have a numbers in moles per liter. Because this is numbers in moles, this is numbers in liter. We just convert it to the liter there from milliliter. If you divide that numbers in moles by the numbers in liter, that is moles per liter number, which is concentration. Okay. So if you do that, it will be 0.1717. So eventually round up. Okay. 0.172. Okay. So you can say moles per liter, or you can say just molarity per liter. Okay. Doesn't matter. It's the same. Okay. So I just stop here today. But definitely.